Okay, so I'm going to talk about a topic in Chapter 3 called Modulation Bandwidth, and I'll try to show you this clearly. I'm redoing a couple videos here, and so what I want to do is I want to start with sort of a general picture of our optical system. We start off with a signal source, and we have an electrical signal, and then we have an optical transmitter, which creates an optical signal. The optical signal goes through the channel, remaining an optical signal, and we finally have our receiver, which converts that optical signal back into an electrical signal. And what I want to do is I want to look at the frequency response of this end-to-end system as an electrical system. So what I'm going to do is I'm going to plot the AC current, I, and I'm going to make a plot that shows that this current starts off with some amplitude I naught, and then in general what's going to happen, depending upon the frequency, the current at the output will have less of an amplitude. And so what we're going to see on the output is something maybe like this, where we have I naught prime on the output side. And basically what happens, and is a very generic characteristic of systems, is that we have a frequency dependent response. And generally speaking, as we go to higher frequencies, we lose the ability to get the signal through the system. In other words, as we go to higher and higher frequencies, the amplitude of the output signal goes to zero. And that's what I'm going to show you here, and we're going to quantify that with a frequency dependent loss. Okay, and the modulation bandwidth is a quantity which characterizes that frequency dependent loss. Okay, so what we'll do is we'll go ahead and write this input signal, the AC signal. The current is a function of time, is the I naught sine of omega t. Omega is now the frequency of this input current. This we're considering it as an analog sine wave here at this point. And then on the output side we'll put I prime of t. We'll call this I prime, and that's I naught prime sine of omega t. Okay? And what we're going to do is we're going to then say that the electrical power at the input is I naught squared times RL, where L is some load resistor, and the electrical power at the output, P elect prime, is I naught prime squared times some load resistance. Okay? And what we're going to do is then we're going to write down a frequency dependent loss, L sub f, as a function of frequency, and we'll write it like this. L sub f as a function of frequency is P electrical prime, the output power, over the input power, P electrical. Okay, so the primed quantities are on the output, so this is output over input, and generally speaking the output power on the output is less than the output power in the input, okay, because of this frequency dependent loss. And what we're going to do is we're going to model this as a Gaussian. Okay, so this is a frequency dependent loss, and we're going to model this with a Gaussian response, and I'll label this as a Gaussian response model. And we know what a Gaussian looks like. It's e to the minus some constant times our variable squared. And here this is a Gaussian response in the frequency. So the larger the frequency, the smaller this term. Okay? And so this is our loss. We're going to go ahead and rewrite this. Instead of having a constant here, we're going to go ahead and write that constant in a way that makes some sense. We're going to write e to the minus ln 2 natural log of 2, and we're going to write f over f 3 dB quantity squared. And this f3 dB is our 3 dB modulation bandwidth. And what we're going to do is we'll just plug in, let's plug in f is equal to f3 dB, and we get LF evaluated at f3 dB is equal to I get a 1 here, I get e to the minus ln 2, which is 1/2. And so this f3 dB is called the electrical 3 dB modulation bandwidth. Okay? It's called a bandwidth because it's a frequency. And it's equal to the frequency at which the response, the output response is half the output power is half that, 1/2 the DC value. Notice that when I plug in f equals 0 here, I get 1. So at DC I have no loss. That's why it's the frequency dependent loss. Okay, so this is the basic definition of the 3 dB bandwidth. And what I'll do now is I'll go ahead and turn this loss value into, so far this loss value is a linear quantity, and we've got the sign convention that a loss value of less than 1 represents a real loss. What I'm going to do now is I'm going to go ahead and turn this a decibel loss value, and we're going to go ahead and use the sign convention that positive losses sign convention. So actual losses are represented by positive dB values. So what we'll do is we'll use that definition. We'll go frequency dependent loss in dB units. We'll put a little dB down there to label it. As a function of frequency is going to be minus 10 log 10 of the power ratio, P elect prime over P elect. Okay, and we can just plug in. So this minus here represents that positive sign convention. So this is minus 10 log 10. Let's go ahead and plug all this stuff in here. E to the minus ln 2 of f over f 3 dB quantity squared. Okay, and what we're going to do is we're going to use the fact, we're going to note that we've got a log base 10 and I've got an exponential here, so I need to change bases, and I'm going to use the fact that log based a of x is the log based b of x over the log based b of a. So I'll use this fact here and rewrite this as minus 10 natural log of e to the minus ln 2 times the quantity frequency ratio squared over ln 10. And this gives me 10 ln 2 over ln of 10 times, and now I have the natural log of e raised to a power, and so I have f over f 3 dB squared. Now this term turns out to be 3 3.01, and this is the origin of that nice 3 dB rule. And so we finally have that this is equal to 3.01 times f over f 3 dB quantity squared. Okay. And what I'll do then is rewrite that finally. And this is our equation. LF in dB units is equal to 3.01 f over f 3 dB quantity squared. And I'll put a circle around that one. Okay. Notice that if we evaluate this equation at f, now I messed it up. Okay, well, you can still read it. If I evaluate this equation at f3 dB, at that frequency, I get 3.01 f3 dB over f3 dB squared, and I get 3.01 decibels. So 3 dB really does represent a loss factor of 1/2. Okay. The last thing I'll do here to help demonstrate this is to just make a quick plot of the output power, the power ratio, output power to input power as a function of frequency. And we'll first do this in the linear domain, where at frequency 0 we have 0 loss, and we start with a value of 1, and our model, Gaussian model, shows that this is a Gaussian. And if we go ahead and convert this into a loss in decibel units, a frequency dependent loss in decibel units, then using the positive sign convention, we have 0 dB of loss at frequency 0, and we have a parabola going upwards. Okay, and that's this equation essentially, f squared. Loss is proportional to f squared. So this is a parabola. So this is the basics of modulation bandwidth. So this f3 dB value characterizes the frequency that you have to go up to so that you've lost half the power in your signal due to this frequency dependent loss. Thanks.